Ma'am, sorry, my mic. I couldn't unmute the mic. Can
Okay,
I
no,
say?
I guess it is.
Okay, Hamza, just wait. Yes, Coulomb, you try.
Minus 8.85 into 10 raised to minus 12.
Not minus, only 8.85 into 10 to the power minus 12. All right. So that's what we had seen. Yes, correct. This was permittivity value, and the relation with dielectric constant epsilon divided by epsilon naught gives us K. So if you are given the force in any other medium, if the medium apart from air is given to you, then you can use this relation epsilon is equal to epsilon naught multiplied by K. So any doubts from Coulomb's law? Should we move further? See, the next topic is electric field. Now understand what is meant by an electric field. See, electric force, this was the property of two charges. When two charges were kept, then what happened? Both of them applied force on each other. But what about a single charge that is kept? When you have a single charge with you, this single charge has a certain environment around itself. What does this mean? This means that if I have a charge plus Q with me, it must be having certain environment around itself. For example, if I bring a small charge, small Q, I bring this charge near it. So if it is at a farther away distance, it doesn't feel any force of repulsion or attraction. You can predict this using Coulomb's law also. From Coulomb's law also, you have seen that electric force is inversely proportional to square of distance. So it means if you increase the distance, electric force, this gets reduced. If you decrease the distance, electric force, this gets increased. So if I bring up a small plus Q charge, at a certain distance from this plus Q, I'll be able to feel this force of repulsion because both of these are positive. So plus Q and plus capital Q and plus small q. These will be now repelling each other. Why repelling each other? Because these are like charges and like charges do repel each other. Now see, this space around this solitary charge means this plus Q charge in which all the electrical properties can be felt. This field or this confined space is known as electric field. So electric field is basically the space around a charge. If I talk about this small q, if I talk about the other charge, the small q, then it also must be having certain electric field around itself. So electric field is a property of a single charge. It's a property of a single charge means every charge, be it positive, be it negative, has a certain around space around itself where phenomena of electrical activity can be experienced. So that space around the charge in which you can feel the force of attraction, forces of repulsion, that field, that space is known as electric field. So I'll write down the definition also. Electric field, this is the space around the charge. This is the space around a charge in which its electrical properties can be experienced. So if I bring up this charge, if I bring up this small q charge, let's talk about this capital Q only. Let's talk about the properties and field of this capital Q only. Let's not consider any other charge. Now see, if I bring up this small q in the vicinity of this, earlier it was kept away. I have brought this small q charge near this capital Q, means in the electric field of this capital Q. So this small q is allowing me to identify whether this charge is positive or negative. Had it been a negative charge, then it would have got attracted. Had it been a positive charge, then it would have repelled each other, which is the case right now. So this small q is allowing me to know the nature of the capital Q charge. So in this kind of setup, we call this charge, the stationary charge, as the source charge. This is the source charge. This is kept stationary, and this source charge is stationary and it exerts the electric field. So the electric field which we are talking about, we are talking in a reference with this source charge. This generates the electric field which is felt by this small q. So we call this small q as the test charge. This is the source charge and this is the test charge. Now here we will be able to see electric force that will be pushing away. Capital Q will be pushing small q away from itself. Why? Because small q has now entered the space around capital Q, which is the electric field of capital Q. So this stationary charge is known as the source charge, and this charge which is required to know as the nature of the source charge is known as the test charge. So one you have source charge, other you have as the test charge. So just tell me one thing, according to you, do you think electric field is exerting the force? That force is a contact force or a non-contact force?
Non-contact force.
Non-contact force. You can easily see at a certain distance that force is felt. So electric field helps us to identify this concept of non-contact forces. Because had this been a contact force, then what would have happened? We would have required both of these charges to come in contact with each other. Once both the charges would have come in contact with each other, then what would have happened? We would have experienced the force. But now what is happening? We don't actually require the charges to actually be in contact. We can just bring the small q near the capital Q, and we will be able to observe the forces of repulsion or attraction, and that will help us determine whether the charge is positive or negative, or is it experiencing any electric force or is it not experiencing. So to explain non-contact forces, this concept of electric field is required. Concept of electric field is required. Also, you should remember that these electric field which surround a charge, these travel with the speed of light. What is the speed of light? What is the speed of light?
3 into 10 power 8 meter per second.
3 into 10 to the power 8 meter per second. So electric field travels with speed of light. So the speed of light, c, which we usually represent it through speed of light, 3 into 10 to the power 8 meter per second. So this is the speed with which electric field travels. And one more thing that makes electric field different from electric force. In electric force, we required minimum 2 charges. Then only force will be exerted on each other. In case of electric field, if you have a single charge with you, also then only you will be able to observe electric field, because the single charge will be having its certain electric field. If you take a negative charge, that will also be having certain electric field. So electric field, this is the property of at least one charge. Single charge is required. All right, so this is the basics about your electric field. Just note down these points, then we'll see further. Done?
Yes.
So that was the introduction of electric field. Now we have to know what is electric field strength or the intensity of electric field, or you can even say electric flux density. Electric field strength, intensity, or electric flux density. Now see what is meant by this. You have this charge plus Q with you, and you also have this charge plus small q with you. What is the name of this charge plus Q, plus capital Q?
Source charge.
Source charge, and small plus q is your test charge. So your source charge is kept stationary and the test charge is kept moving. Now see what happens. Again, naming just for your confusion, this is your source charge, this is your test charge. So tell me one thing, if small q is brought near this capital Q, will small q experience any kind of force or not?
Yes, sir.
Yes.
Yes, ma'am.
It will experience force. So whatever is the total force experienced by this test charge because of the electric field of the source charge, that is what is known as electric field intensity or electric field strength, you can also say. So whatever is the net force experience, a force will also always be experienced by this charge because of presence of source charge. So electric force is whatever you have studied in Coulomb's law in Tuesday's class. So electric force experienced by this test charge means, what is this test charge, small q? Because of field of source charge. Because of field of source charge, and your source charge is capital Q. This is known as electric field intensity. Now see, how do we write this electric field intensity? Just a representation of electric field of source charge see, it is represented through this electric field limits q, small q means the test charge tends to equal to 0. You have force by the charge. This is how we mathematically represent this line, what I have written. The line, the statement that I have written, no, that electric force experienced by the test charge because of the electric field of the source charge. If you wish to represent this sentence mathematically, then this will be the representation. Now see, I have added this limit q tends to 0. This part. So this limit, just make a note and you can write it, that limit q tends to equal to 0. This shows that whatever is the force exerted by small q. See, two charges are present, plus q is there and small means plus capital Q is there and small plus q is there. So if plus capital Q is exerting force on small plus q, then reciprocal of it can also happen. Means small plus q can also exert force on capital Q. There is no foundation in plus q plus small q that it cannot exert force. So in order to limit that, that's why we have written limitation q tends to equal to 0. Means whatever is the force experienced by this exerted by small q on capital Q, this is negligible. Force exerted by small q, this is negligible So what happens? If force exerted by small q, this is negligible. So plus q doesn't have the reason now to move. So that's why it becomes stationary source charge. That what I was describing to you. Now force exerted by small q is almost negligible. So there won't be force exerted on this, means it won't repel it towards the other side. Small q won't have so much force to move plus q. So now plus q will be stationary, and hence capital Q cannot move. Now capital Q cannot move. So this is how you write intensity. One more thing, electric field is not a scalar quantity the way charge was. So only electric charge is a scalar quantity. Electric force, electric field, both of these phenomena, these are vector quantities. Electric field is a vector quantity. So whatever is the force experienced by test charge, that direction will be the direction of electric field. So I'll write down this point also. Its direction, it is same as that of force experienced by the test charge. So since we are writing force experienced by test charge, force experienced by test charge, so you can write a relationship between test charge, force and electric field as follows. Electric field is force divided by the test charge, one of the charges that is present. This is what is another formula of electric field, that you have force per unit charge. So all of you write me just now in the chat box. You know the SI unit of force, you know the SI unit of charge. What should be the SI unit of electric field? Everyone will write down. Rishan, you also answer. Fatima Munir, Hamza Shekhani, Hiba. Rishan, are you there in the class? Rishan Mirza. Yes, Fatima Munir, just check it. Will it be this much only, or something else will also get added to it? Fatima Munir, you tell me, what is the SI unit of force? Yes, Fatima. We all are waiting. What is the SI unit of force?
Newton.
Newton. And the charge is Coulomb. So you have written only Coulomb. Coulomb is only for charge. So say, yes, rest of you are right. Electric fields SI unit. See, for force it is Newton. For charge, it is Coulomb. It will be Newton divided by Coulomb. Newton per Coulomb. You can write it in this manner also. Okay, one more unit is there of electric field, which we will not discuss it here. It is volt per meters. This SI unit you will be understand when we'll do the second chapter. That is potential and capacitance. From there, you can see how can we write volt per meter. But you have to remember Newton per Coulomb. This is the SI unit of electric field. And electric field, this is a vector quantity. So you cannot add, if there are n number of electric fields present, so you cannot directly add all those electric fields. If there are various electric fields present, then you have to add it using your vector addition. Vector addition includes your various parallelograms law and triangles law and all those vectors law that you have studied. Then also one more thing, if I tell you this was electric fields formula. Now, if I say from this formula only, if I say small q is equal to 1 Coulomb. So Hiba, you tell me, what will be the relationship between electric field and electric force now? If small charges plus 1 Coulomb. Hiba, answer. Anyone else?
Ma'am, electric field will be equal to electric force.
Yes, Krishna. If your charge is equal to 1 Coulomb, so just put it in this formula and see if E is equal to F divided by Q and Q is 1. So E is F divided by 1. So electric field will be equal to what? Electric field will be equal to force. From this, what can we conclude? From here, we can conclude that electric field at any point or at a point, it can also be defined as, this is another definition, can also be defined as the force experience. See why electric field is now equal to the force. So it can be defined as force experienced by what? By this. Unless and until this condition is specified, then only this is applicable. So force experienced by unit positive test charge. Unit positive test charge. Is this clear now? Definition of electric field and what is meant by electric field.
Yes, ma'am.
So just note down these points and we'll do a very simple numerical formula based question. And Rishan, if you're there in the class, just respond me yes or no in the chat box. So all those who have written it, copy this question and send me your answer. This is a very general formula based question based on electric field.
I don't know how to solve this.
See, electric charge is given. You have electric force given, and you have to calculate electric field. Just look into your notes. You must have written a relationship between charge, force, and electric field. Okay, Hamza, tell me what is the charge given? Yes, Krishna, your answer is correct. So Krishna has answered first.
10 raised to minus 3 coulomb.
Correct. 10 to the power minus 3 coulombs. And what is the force given?
Force is 10 raised to 2 Newton.
10 to the power 2 Newton. And just tell me a relationship between, no, Fatima, just check once again. Akifa, you are right. Fatima, just check once again. And tell me a relation, just look into your notes. Just tell me a relation between charge, force, and electric field. We have done it right now, Hamza. This
Electric field is equal to force by
charge.
charge.
Okay, so you have force with you have charge with you. So will you be able to now calculate the electric field?
Yes.
Just check, just see what's your answer coming, Hamza.
Okay.
Fatima, resend your answer. Rest of you also answer. Kulsum answer. Hiba answer. Yes, Hamza, correct. It's correct. So correct answers have been given by Hamza, Akifa, and Krishna. See, force is given to you as 10 to the power 2. Charge is given to you as 10 to the power minus 3. Now see, 10 to the power plus 2, and this, when this 10 to the power minus 3 will go up, it will become 10 to the power plus 3. So what is this? 10 to the power 5, and the SI unit will be Newton per Coulomb. So all those who have committed error, just see where was your error in your calculation and note it down. Then we'll move further.
Teacher, my error was not in the calculation. Instead of 10 to the power 2, I wrote it as 10 to the power 5.
Oh, 10 to the power 5. That's why your answer was coming in powers of 2.
Yeah.
Okay. I think by now you all must have written it down. This was a one-liner answer. Now electric field for a point charge, the derivation of this is very easy because you know what is electric force and now you know what is electric field. So whatever you have as electric force, if you divide it by Q, that will give you electric field. So see, if you have a source charge with you, let's say this is the source charge. It is separated by some distance, let's say r vector with to this small plus q. So small plus q is your test charge. So this will be experiencing an electric force. Electric force, why? Because of source charge. And since source charge is generating electric field is in the direction of electric force. So electric field will also be over here. Now see, if you remember electric force from your Coulomb's law, who is going to tell? Fatima Munir, you tell me, what will be the electric force using Coulomb's law? Yes, Fatima Munir. If you have two charges separated by a certain distance, now how do we write the force?
KQ1 Q2 by R square.
K Q1 Q2 by R square. No, see, Fatma, this will be K. First charge is capital Q. The other charge is small q divided by R square. This is using your Coulomb's law. Just revise whenever you come. Revise whatever we have done in the previous class. So this using your Coulomb's law, that's what we have seen in Coulomb's law. No, electric force was directly proportional to the product of the charges. So first charge is your source charge, the other charge is your test charge, inversely proportional to square of separation between them. So you have here as the separation small r. Now see one relation that we have seen. Let's write it in terms of limitation only. Electric field limit Q tends to 0, force by charge. Now see, if you put everything, the formula of force, whatever is the formula of force into this, electric field will be equal to what? Limit Q tends to 0. Force was K capital Q small q by R square. And here you have this test charge with you, small q with you. So small q gets cancelled. So electric field becomes limit q tends to 0, k q divided by R square, or in simpler terms, the way we have written it for electric force. See, force is what? K capital Q small q divided by R square. So electric field will be what? Just divide this term by small q because you are dividing it for this test charge. So if you divide it by the test charge, what is left? K capital Q divided by R square is left. Or if you can write in terms of the full formula of dielectric constant, it will be Q divided by 4 pi epsilon naught R square. So the derivation of electric field is very easy. You know where is the electric force. Once you know what is the electric force, you can easily say you just divide it by the charge, it gives you the formula of electric field. Regarding the direction for positive and negative charges, just remember this carefully. If you have a positive charge with you, if you have, or let me write it as, for positive charge, because this will be utilized when we'll draw electric field lines also. So remember this, for positive charge, electric field, this is away from the charge. This is away from the charge. Electric field will be away for a positive charge. And just the opposite of it, if you have a negative charge, then electric field will be directed towards the charge. is towards the charge. So towards is for negative and away is for positive. Like if I give you this example, plus 2 Coulomb charge is there. Now see, I have taken a point over here. This is point A. This is plus Q. So see, 2 Coulomb is there, a point has been taken and 2 Coulomb charge is placed. So if I go towards it, this will be the direction. And if I go away from it, this will be the direction. Mean right hand side will lead me away from the charge and left hand side will lead me towards the charge. So since it's a positive charge, for positive charges, we run away from the charge. If you run away from the charge, the direction will be in this. This will be the electric field at this point. If I take a point over here, let's say this point is B. Since the charge is positive, you have to move away from the charge. If you move in this direction, in the right hand side, similar to A, it will lead you towards the charge, but we don't want this. We want to move away from the charge. So this means electric field will be towards the left hand side. This will be for EB. If I take a point over here, Akifa, you tell me, what will be the direction of electric field for point C?
Upward.
Upwards, correct. See, if you move away from the charge, it will be in this direction only. This will be direction of electric field. Similarly, if you take a point over here, then electric field will be away. This will be ED. That's how you take electric field. If you have another point, just move away from the charge. That will give you direction of electric field for a positive charge. If I take another case, instead of plus 2 Coulomb, I have taken minus 2 Coulombs. Now I have taken a point A. So Krishna, you tell me, what will be the direction of electric field?
Ma'am, towards the source charge.
Towards the
Towards
charge. So left or right?
Left, ma'am.
Left hand side, correct. So if you will move towards the charge, this will be the direction of electric field. Similarly, if I take a point B, I have to move towards the charge. Why am I moving now towards the charge? Because it's a negative charge. So this will lead me towards the charge. Another point, C, downwards will be the case now. Why? Electric field for this point C will be towards it. If I take a point D, moving towards it will lead me the direction for a negative charge. Is this clear?
Ma'am, we are considering the points as positive, right?
Yes. Point charges we are taking. The test charge can be anything. You don't require the test charge because test charge, as you have seen in the formula also, it gets cancelled. So you are only concerned with the source charge because source charge is enough to produce electric field. You don't require any other charge for electric field. Had it been electric force, then we would have considered what is the sign of the test charge. Here we are just taking points. These points are not charges. These are simple point where no charge is present. And we are calculating, we are just taking the direction of electric field because of presence of the charge that I have taken, minus 2 Coulomb or plus 2 Coulomb. All right. Okay, if you remember, let's see who remembers. Yes, Hamza. Hamza, you have come just now, no?
Yes, ma'am. I come from school just.
Okay, it's okay. Hamza Shekhani, you tell me. If electric force was there apart from air, means in some other medium, which quantity did we use? Which quantity did we use? If we have yes, say Hamza. If you have a different medium, then how do you use it? Instead of air, if you have. Yes, Hamza?
I don't know.
See, anyone else who remembers it?
You can use E.
Yeah.
Okay, Fatima, you say.
You can use E instead of E naught.
Epsilon is the symbol we can use epsilon naught. See, if force in other medium, Hamza, just listen it carefully. If you have this as k q1 q2 divided by r square, so here k is k over here is 4 by epsilon naught. So Hamza, see, if you have a different medium, what you can use for a different medium, you have to put this constant k with you, 4 pi, not only epsilon naught. You have to use epsilon, and epsilon is k epsilon naught. So you have to use k epsilon naught r square. Is this clear, Hamza?
Yes, teacher.
Okay, if you have a medium air, then you have to use k q1 q2 divided by r square. If you are taken a different medium, then what you have to do? You have to write epsilon, because epsilon naught is valid only for air. So if you are taken epsilon naught, epsilon, then you can use this relation epsilon is equal to k epsilon naught. So if you are given a force in any other medium, whatever is the value of dielectric constant given to you as 3, 4, 5, 6, whatever, just divide whatever force has been come in air to the dielectric constant. Similar is the case of electric field also. So in electric field,
K is 1 by 4 pi epsilon 0, right?
yes, k is 1 over 4 pi
So,
epsilon naught.
so if for 1 by 4 pi epsilon 0 into K, that is epsilon.
See, this is epsilon. This symbol is epsilon. This is absolute permittivity of free space. It helps us in deciding whether how the force is dependent on a particular medium. So for different media, we have different values of epsilon. For example, for air, we have 8.85 into 10 to the power minus 12. So just to specify it for air and make it unique for air, we write it as naught. For any other medium, you can take it. For example, if you have glass, so you can take it epsilon for glass. If you have a different medium, you can take it epsilon for water. Every value will be different. Just we have to remember it for air, that is 8.85 into 10 to the power minus 12. You just have to remember it for air. And k is what? K is 1 over 4 pi epsilon naught. So when you put the value of 4 multiplied by pi multiplied by this air's value epsilon naught, then you get k as 9 into 10 to the power 9. This is what is the constant. This is only for air. Now if you change the medium, if I take those charges which were present in air, if I put them in water, let's say I've taken the medium, I've changed the medium. So dielectric constant for water, it will be different. So what we do, we use this relation. Here now epsilon naught won't be used. Epsilon will be used. Epsilon for water will be used. So epsilon for water can be written as a k multiplied by epsilon naught, because we only know the value for air. So if we want to relate it to air, we can multiply the value of k with epsilon naught. That will give us epsilon in any other medium. Hamza, is this clear? Any doubts?
Okay.
Okay. So electric field in air can also be written as Q divided by 4 pi epsilon naught r square. And if I change the medium, so what will happen? For any other medium, I have to write it as 4 pi epsilon, because epsilon naught is valid only for air. And for epsilon, I have this relation as epsilon is equal to epsilon naught k. So it can be written as 4 pi epsilon naught k r square. This is valid for any other medium. Is this clear to all of you?
Yes, ma'am.
Direction of electric field and everything. Just note it down. If you have doubts, you can ask me. For direction, you can use those unit vectors which we have, I cap, j cap, k cap. If anybody gets the answer, then send me. Yes, first answer has been submitted by Akifa and it's absolutely correct. Rest of you also tried. It's a very easy question. You know how to calculate, how to take the direction for a positive charge. You have charge as plus 10. You know the separation between the point and the charge that is given to you in coordinate form. And you know the value of the constant k. So only Akifa has submitted. Any other else is submitting the answer, or should I discuss now?
Could you please discuss because I don't know how to do it.
Okay, Hamza, I'll help you. See, you have a point charge present placed at the origin. Yes, Krishna. Krishna is also correct. Akifa and Krishna both are correct. See, you have Hamza. Listen, you have the origin, and rest of you also who were not able to answer. Just see, at the origin you have this charge plus 10 Coulomb present, and it says at a point A. This is the point A. 3, 0, 0. See, whenever this is given in this form, first one means x-axis, second one means y-axis, and the third one means z-axis. This is how it is written. So if it says 3 meters, 0y, 0z means there is no coordinate axis of y, there is no coordinate point of z, only x is given to you as 3 meters. So if this is the origin, this will be your x-axis. So Hamza, you tell me, what will be this separation then? If this is your x-axis?
3.
Yeah, 3, correct. This will be 3. Yes, 3 meters. Now see, the formula of electric field. In short, if I write, it is kq divided by r square, which is easy to remember. We can elaborate it later on. Now see, k, what is the value of k? Anyone?
1 by 4 pi epsilon 0.
Yes, if we put in the values of
9 into 10 power 9.
yes, Fatima. See, Hamza, when you put in the values of 1 by 4 pi epsilon naught, you get it as 9 into 10 to the power 9. So what happens in most of the questions, wherever we have to substitute k, we write it as 9 into 10 to the power 9 only. That will ease our calculation also, and that will help you to remember. Because see, no other medium is given, nothing is mentioned. So you can take k as 9 into 10 to the power 9. And charge is given to you as 10 coulombs. And the radius means not the radius, let's say the separation between the point and the source charge. This is given as 3 meters. So you have all the data with you. Data is sufficient. What you have to do, you just have to place it in this formula. So instead of K, I will write 9 into 10 to the power 9. For charge Q, I can take 10 and R square. R square means 3 square. So this gives 9 into 10 to the power 9 into 10 divided by 3 square is 9. So 9 gets cancelled. 10 to the power 9 into 10. This becomes 10 to the power 10. This is 10 to the power 10 Newton per Coulomb. This is the magnitude. Is the magnitude clear to all of you?
Yes.
Yes, ma'am.
Okay. Now see, we have to find out the direction also. As I've told you, just remember, see the way I have given you plus 2 Coulomb that time and I gave you a point A. How did we calculate the direction? We had taken ourselves away from the charge. Similarly, when you consider the direction of electric field at this point, now this is positive charge. So remember, whenever positive charge is given, you have to move away from the charge. Moving away from the charge will lead you in which direction? This is your positive x-axis. This was positive x-axis. That's what we had seen. No, 3 comma 0 means 3 meters is on x-axis. So moving away from this direction will lead you over here. This will be the direction of electric field. Is this clear? If you move away from the charge, had it been a negative charge, we would have moved ourselves towards O, towards the source charge. Now we have to move ourselves away from the source charge. Now see, you have unit vectors as I cap minus I cap. For positive x-axis, you write plus I cap. For negative x-axis, you write minus I cap. Similarly, for a positive y-axis, you write plus j cap. For negative y-axis, you write minus j cap. For positive z-axis, you write plus k cap. Letter k comes. And for negative z-axis, you write minus k cap. So Hamza Shekhani, you only tell me, if this is the direction of electric field, which unit vector should I use?
X.
X-axis is the axis. So if you have a positive x-axis, you have I cap. See, for positive x-axis, you use the unit vector plus I cap. Had it been a negative x-axis, then we would have written minus I cap. So this is how we represent the magnitude as well as the direction of electric field. Now is it clear?
Yes.
Yes.
Okay, just note down the solution. Then we'll see certain graphs of electric field.
So what is it for y-axis?
Okay, let me just write it down. That will help you remember. See, if you have x-axis, so for positive x-axis, you write I cap. For a negative x-axis, you write minus I cap. For y-axis, had it been moving upwards, the direction would have been upwards. Then see, for positive y-axis, you write j cap. And for negative y-axis, you write minus j cap. Similarly, for z-axis, the letter k comes. So for positive z-axis, it will be k cap, and for negative z-axis, it will be minus k cap. So by just looking at these unit vectors, I cap, j cap, you will be able to identify whatever is the direction.
Ma'am, in the example like 1.6 of the book, they have used this vectors. So should we do that?
What, Zeb? Can you repeat?
In the example 1.6 in the textbook, they have used this which vector it's going in which axis.
Yes. Yes, that is also correct. In case instead of ICAP also, see, this was a subjective question. So I have used ICAP, which represents both of it. So you can use it however you want to. You can specify towards this direction, towards that direction. You can specify using your vectors. So using these ICAP, JCAP also, it becomes easier. So it's up to you. So written, all of you?
Yes.
Yes.
Okay, if anybody is writing, can stop me. Otherwise, let's see some graphs. Okay, what are graphs? Graphs are basically what you have studied. We have the same graphs. Graphs are only pictorial representation of any function. If you have to represent variation of two quantities, how a quantity is dependent on the other quantity, that's where we use graphs. So graphs are pictorial representation of function, any functions. Now see, just revising your basics, most of you know this, just revising it, you all know that there are various types of graph. One, you have a straight line graph. Majorly 3 kinds of graphs will be used in your syllabus. First, you have the straight line graph. Straight line graph is used in case of linear equation. Linear equation means when one variable is directly dependent on the other and has the power 1. Not power 2, not power 3, or not any other value apart from 1. So in this, what happened? If I increase x by 1 unit, then y will also get increased by 1 unit. If I double x, then y will also get doubled. If I triple x, then y will also get tripled. Why? Because they both of them are linearly dependent on each other. So if this is a graph between x and y, this is how it will come. Straight line. A graph between x and y. This shows linear dependency of the graphs. Another type of graph that you have are the parabolic curves that you get. This is valid for quadratic equations. Quadratic equations means y will still be proportional to x, but now the power of x won't be 1, it will be 2. So wherever you get such a case, any power, any quantity is proportional to other quantity with power 2, you get the parabolic curve. And parabolic curves are represented like this. If y and x are given, this is how you represent a parabola, where y is proportional to square of x. Then one more type of graph that will be used in your syllabus. These are the hyperbolic graphs. See, in this, whenever the quantity is inversely proportional, in previous 2 cases, the quantities were directly proportional. In this case, the quantities are inversely proportional. So y is inversely proportional to x, or y is inversely proportional to x square, or y is inversely proportional to 1 by x cube, and on so on. So this, the plotting of this graph, this is y, this is x, hyperbola is in this manner. So these are the basic graphs that you have already studied in your previous classes, just a basic revision of it. Now see, regarding your syllabus, if I give you this example to plot, let's say first part, force versus R graph, means force versus R square graph or R graph. This one for Coulomb's law. And okay, let's first discuss it. Now see, F is proportional to R. How? F is equal to K Q1 Q2 divided by R square. So is F directly proportional to R or inversely proportional to R?
Inversely proportional.
Inversely proportional to R. So F is inversely proportional to R square. Whenever you have such a situation, do one thing, just substitute one quantity as Y, other quantity as X. If I substitute F as Y, R as X, this will be Y inversely proportional to X square. Is this case only?
Yes, sir.
Yes. So the graph in this case will be a hyperbola if you are given F versus R. So if this is the separation distance, this is the force, this is the inversely proportionality showing you the parabolic graph, hyperbolic graph where F is inversely proportional to R square. Now see how the difference comes and how the questions become difficult is that this was the first part. If the example second part I take it as F versus 1 by R square graph for Coulomb's law only. Now see here it gets confusing. This looks similar to the previous part, but the answer is completely different. What I have told you, just substitute one quantity as Y, other quantity as X. Your formula of force, electric force using Coulomb's law, it was K Q1 Q2 divided by R square. What is Y? Y is F. So if I write force as Y, now let us see how it is dependent on 1 by R square. Now you don't have to take R square. This may get confusing. Just listen it carefully. 1 by R square means 1 by R square. This quantity, take it as X. If you take 1 by R square as X, it will be here. See, X, K, X, Q1, Q2, K. Let's substitute the values which I have taken. Instead of Y, write F. Instead of X, write 1 by R square. K, Q1, Q2, you are getting it back. So means Y is directly proportional to X here. It means F is directly proportional to 1 by R square. F is inversely proportional to R square, but F is directly proportional to 1 by R square. Is this
So it will be a slope?
It will be a straight line, linear proportionality. So the graph will be in this manner only. 1 by R square is given to you. Just look at the questions carefully. If you are given, so a straight line graph will be there if it is for a force. So this was for Coulomb's law. Similarly, if I give you for electric field. Okay, let me repeat it once more. First part is clear? This one?
Yes.
Let me repeat it for the second part. See, force is K Q1 Q2 multiplied by 1 by R square. Are you satisfied with this, what I have written, Fatima?
Yes.
Okay. So as I've told you, whenever you are getting confused, know how to plot the graphs. Take one quantity which is dependent as Y. So force as Y I have taken. And the other quantity which is the independent quantity which you are given. What were we given? We were not given R. Had we given R, we would have taken R as X. So it would have become Y is inversely proportional to X square. But now see, it is not saying X is R. X is R was for the previous case. Now you have it as 1 by R square. So 1 by R square, take X as 1 by R square. That's it. That is what the other quantity is given to you, no? So if I write it as K, Q1, Q2, X. Are you satisfied till here? K, Q1, Q2, X?
Yes.
K is a constant. Charge's magnitude will remain same. So Y is directly proportional to X. What was Y? Y means force. What was X? X was 1 by R square. So force is directly proportional to 1 by R square. That's why force is inversely proportional to R square. No. If it is proportional to 1 by R square directly, then only we say force is inversely proportional to R square. So this is a linear This is a direct case, direct relationship case. This is f. Had I taken r, then it would have been a hyperbola because it is inversely proportional to r square. Now it says 1 by r square. This is the condition. So it is a linear graph. Is this clear, Fatima?
Yes, teacher. Thank you.
Okay. If I take another example to plot E means electric field versus R graph, and the charge is a point charge. Then see, E is what? E is KQ divided by R square. So E is your one quantity means Y. Other quantity is R square. So let us write KQ. Let's substitute X square. So K is a constant. Charge magnitude will remain same. Y is
Hyperbola.
hyperbola, correct. Inversely proportional to x square. So this is the case of hyperbola. So if the graph is given to you, if you are given the graph to plot, this is the radius, this is the separation, this is the electric field, this is how electric field will fail. Clear to all of you?
Yes.
Now, just note it down. Is it clear to all of you? Hamza, Hiba, Krishna, Kulsum?
Yes, ma'am.
Teacher, can you show the second one? The above one of this one.
This one?
Yeah. Okay, can you scroll a little bit?
This is just the repetition I was telling you. So don't copy this one if you have copied this one. Straight away write it for electric field versus R.
Yeah, okay, I'm done.
So all those who are done, you can leave the meeting. This is for today. So thank you. We'll continue in the next class.
Thank you, teacher.
Thank you, ma'am.
Thank you, ma'am.
Okay, most
Thank you,
welcome.
ma'am.